Hello everyone, welcome to today's webinar brought to you by Microbial Insights on enhancing in situ denitrification. We appreciate that you are taking the time to join us today, and it is my pleasure to introduce our esteemed speakers, Dick Raymond and Dr. Michael Lee. Dick Raymond is the president of Terra Systems, and during the past 40 years, he has designed and managed numerous successful in situ and ex situ soil and groundwater remediation projects in the US, Brazil, Japan, Taiwan, and even Europe. Dick co-founded Biosystems Inc., the first environmental bioremediation company in the United States in 1984. The other co-founder is Dick Raymond Sr., who authored the first in situ bioremediation patent in the US in 1972. So working together, Dick Raymond Jr. and Sr. proactively commercialized practical aerobic bioremediation technology solutions in the 80s. So during the past 2 decades, Dick Raymond Jr. has been an active participant in the development of advanced anaerobic bioremediation technology solutions. Dr. Michael Lee is the Vice President of Research and Development at Terra Systems, and he has a Doctor of Philosophy and a Master's of Science degrees in Environmental Science and Engineering from Rice University, and a Bachelor of Science degree in Biology from University of Louisiana at Monroe. So Dr. Lee has over 35 years of experience in the field of bioremediation with expertise in applying in situ anaerobic bioremediation of chlorinated solvents and metals, implementing in situ aerobic bioremediation of hydrocarbons and other contaminants in groundwater and waste impoundments, conducting biodegradation and chemical oxidation treatability studies, and assessing natural attenuation of organic contaminants at over 200 sites. So he jointly holds the patent on the use of emulsified soybean oil to support complete reductive dechlorination of chlorinated solvents, and he has published over 100 articles and abstracts in peer-reviewed journals, conferences, proceedings, or books. So now, before I let Dr. Lee and Mr. Raymond take it away, I would like to remind you all, as always, this webinar is being recorded and will be available in the resource section on Microbial Insights website by the end of this week or even by the end of today. So don't worry, we'll also be sending out an email with a link and a certificate of attendance following this webinar for those that have registered. There will also be some included informational. If you look in the handout section on your sidebar, you can see some handouts there. After they are done speaking, there will be a time for questions, so feel free to type your questions as the presentation goes on, and either I or Dora will try to read off as many as we can when that time comes, so that way they can get you your answers. Join us in welcoming true advocates for sustainable solutions, Dick Raymond and Dr. Michael Lee.
Okay, thank you, Marshall. I appreciate that. And welcome everyone to our presentation. First of all, Mike and I would like to acknowledge and thank our co-authors of this presentation, Tim Pack and Paul Dombrowski. Tim is a senior remediation engineer with Terra Systems, and Paul is a senior remediation engineer with Isotech, which is a technology field implementation company. I'm going to cover some of the basics, and then Mike will take us through the development process for the substrate that we're using for denitrification. If we can get the slide to change. There we go. First, a little background on Terra Systems. We are celebrating our 32nd year in business. However, as Marshall alluded to, we trace our roots back to the 1950s when Dick Raymond Sr. started looking for petroleum degrading bacteria in West Texas. And that led him to developing in situ biotechnology in the early 70s, which resulted in the patent that Marshall mentioned. My father, Mike, and I participated in the first anaerobic in situ bioremediation project while we were at DuPont during the last century, which was 1992. And then, of course, as Marshall mentioned, Mike co-authored the first EVO patent for remediation of chlorinated solvents in 2002. Our core competencies include our own manufacturing plants in Delaware, Taiwan, and Japan. That enables us to produce custom formulated products as well as controlling the quality of our products. R&D is also a key part of the core. Our in-house treatability lab enables Mike to develop new products such as the one that we're using for denitrification projects. And of course, I have to point out that our products are both green and sustainable, since bioremediation is one of the original sustainable treatment technologies. We've been advocating for sustainable remediation since our founding, and we are one of the original founding members of the Sustainable Remediation Forum, otherwise known as SURF, which started back in 2006. Okay, enough about our background. Let's move into some of the basics that we're going to be talking about today. Eutrophication is a general term which describes a process in which nutrients accumulate in the body of water, resulting in increased growth of microorganisms that may deplete the water of oxygen. And that leads to excessive plant growth and algal growth due to the increase of limiting growth factors. And those are primarily nitrogen and phosphorus. We're seeing that in increasing numbers of surface water bodies because of the accelerated rate and extent of human activities. And it's coming from not only point source discharges, but also non-point loadings of limiting nutrients, such as the nitrogen or the phosphorus. Of course, the environmental impacts lead to dense blooms of noxious, foul smelling phytoplankton, and that in turn limits the light penetration, which reduces the growth of submerged vegetation. We also see elevated pH and also end up with anoxic dead zones because of the decomposition of the algal mass. We first started this with because of Cape Cod, attending a conference up there in about 9 years ago. It became apparent that Cape Cod has significant problems with algae blooms in their 800 or part of their 890 ponds on the Cape. Septic systems are used for approximately 85% of the wastewater treatment on the Cape. And those systems are typically Title V septic systems, which are permitted by local boards of health. And the downside to those old systems is that they were designed to remove pathogens and not nutrients. As a result of the bacterial reactions in the septic tank and in the aquifer, transforming organic nitrogen to ammonia and then to nitrate, they ended up with large dilute nitrate plumes that flow into the coastal waters, resulting in eutrophication. And of course, then you have poor water quality, loss of habitat, and both aesthetic and economic impacts. The Cape Cod's nitrogen path has been a torturous one over the last 9+ years. The original cost estimate to sewer or put sewers into the entire Cape ranged from $6 to $8 billion, and the politicians couldn't see that they were going to be able to afford that, so they started looking for ways of reducing that cost, which meant reducing the number or the amount of sewering that they needed to do. An interim measure or evaluation rather lowered the cost to somewhere between 4.6 and 6.2 billion. Please remember that these numbers were generated probably about 5 to 8 years ago. And then the latest update, which includes some sewers, but also includes non-traditional treatments, lowers that cost to somewhere between 2 and 3.8 billion dollars. And that's a combination of sewer infrastructure in the high density areas, along with in situ groundwater treatment with permeable reactive barriers. There's also a lot of work looking at innovative and alternative septic systems, which have the ability to knock down the nitrogen coming out of them. And then they're also looking at shellfish in aquaculture. Of course, the goal is to minimize the proposed areas of towns and properties that are going to need the very expensive sewers. Denitrification, of course, is a very well understood process for wastewater treatment. Bacteria convert the nitrates to inert nitrogen gas. The denitrifying bacteria, of course, are ubiquitous in the soils, and they're also anaerobes. With PRBs, it's been an accepted groundwater treatment approach for a couple of decades now. The groundwater, of course, flows through the barrier. It's reactive in that it promotes biological denitrification. And of course, the barrier prevents nitrate migration to coastal waters. I won't bore you with this nitrogen and denitrification path. Please understand that the nitrogen cycle is well understood. You also might note that NIRS and NIRK genes are involved in the conversion of nitrate to nitric oxide. Of course, there are other genes involved in nitrification, denitrification, ammonification, and Anammox nitrogen cycle. In other words, there's no single gene out there that is involved in the nitrogen cycle. This is a summary of Microbial Insights denitrification genes field database. There are, as you'll notice, anaerobic ammonia oxidizing nitrate reducers, archaeal nitrate reducers, and bacterial nitrite reducers, sorry. The bacterial NIRK and NIRS genes are the most abundant, with up to about 10 times 8 cells per mil on average. And these genes were found in about 50% of the samples analyzed for denitrification genes in the Microbial Insights work. Now I'd like to turn the presentation over to Mike Lee, who will take us through the development of the substrate that we use in situ denitrification process.
So we're going to be talking about some bench scale testing that we had done, looking to evaluate multiplied vegetable water EBO to support denitrification, looking at the effectiveness of the material, the persistence of the EBO, and then migration, which is a community concern. So the first column test that I'm going to talk about is one that we use soil from a site in Falmouth, Massachusetts, using an off-the-shelf SRS. So it's a small droplet material with nutrients. So we had 3 columns with 2 loadings of EBO, and then the third column had a combination of EBO and ZBI. And we saw breakthrough of the EBO through the columns. These are relatively short, about 3 feet long. But we did see complete removal of the nitrate pretty quickly after the introduction of the EBO, and that lasted for a little over 350 days. And then when the TOC concentrations in the effluent reached about 4 or less than 4 micrograms per liter, we started to see breakthrough of the nitrate. So we had questions of how to make the EVO last longer, and can we make the EVO stickier so less of it is transported. So next we did some additional bench testing. We adjusted the properties of the EVO for higher flow aquifers using a larger drop bit size, anionic surfactant rather than a non-ionic surfactants of the SRSSD. We didn't add any sodium lactate in these columns, and that product is the SRS-NR. We connected the 3 columns, so we had a total length of about 9 feet of column, and increased the flow rate up to about 1.9 feet per day. We didn't see any evidence for the emulsion moving through the column, and we're able to sustain nitrate removal at concentrations of nitrate down as low as 2.9 milligrams per liter of TOC. And we saw better retention of the SRS-NR on the soil matrix. The second one, we're concerned about what happens with acidic conditions that are found sometimes on the Cape. So we had another column study with 3 columns, one without any buffer, one that had 0.05% of a fine calcium carbonate, and then the second or the third column had 0.25% of a fine calcium carbonate. And that's on the basis of soil loading. And then we acidified the influent with the hydrochloric acid. And you can see the influent pHs in blue, you know, dropped down to as low as 3 milligram or 3 units. Column 1 in black, the pH range typically from between 6 and 7. And then we do see an impact of the in column 2 with the 0.05% fine calcium carbonate, higher pH above 7, and then about 30 days it began to drop down into the 6s. And then that highest loading maintained the pH above 7 in all cases. And then on the right, you see the influent concentrations of nitrate, you know, between 5 and 9 milligrams per liter, and then that was consumed within a couple of days and maintained for over the period of the column study, which was about 90 days. So in this particular case, we don't see that big of impact on pH, but we would typically recommend that you add some either calcium carbonate or sodium bicarbonate just to make sure that you don't get into really acidic conditions. And then the final column test is one that we performed with Veronica Gonzalez of Tufts University. She's trying to develop a kinetic model for the process. So this was a small column with only about 0.5 feet long. Its flow rate's really high, about 6.5 feet per day. So the retention time on the column is less than the 10th of a day. And then we added about 5.5 grams of the SRS-NR. So we're looking to see, you know, how long it could be sustained. We see influent concentrations of nitrate in the light blue between 20 and 30 milligrams per liter. DOC concentrations or TOC in the effluent reached a maximum of about 80 milligrams per liter immediately after the introduction. And then we see the TOCs drop down into the 0 to 10 milligrams per liter after about 200 pore volumes. And after about 250 pore volumes, we'll begin to see in the dark blue the nitrate and the effluent begin to come up. So, you know, that low concentration of TOC wasn't able enough to sustain complete denitrification, but we still see, you know, roughly 20 or 15 milligrams per liter of the nitrate being removed, even at that low TOC concentrations. And so Veronica Gonzalez published a paper in Environmental Engineering Science on a process-based model to describe this. So PRBs intercept and remove nitrate from the groundwater. As you can see, septic sink and leach field, the nitrate plume moves down into the groundwater, and we're proposing to add a PRB to intercept the nitrate plume and treat it before it reaches the ocean body. There are a variety of different carbon substrates that can be used for anaerobic degradation of nitrate and chlorinated solvents. So they provide food for the bacteria and consume oxygen and the other competing electron acceptors. They're soluble materials such as lactate, methanol, molasses, high fructose corn syrup. These are water soluble but are consumed rapidly, usually within 1 to 3 months after the addition. Slow release substrate, things like emulsified vegetable oil, lecithin, or neat oil are going to last a lot longer. They're hydrophobic. Emulsified vegetable oils are relatively easy to distribute. Lecithin is a very viscous material, and so it's a lot harder to work with, and it's going to be stickier. And then the neat oil is a possibility, but what we found is that it tends to float and doesn't give you nearly the distribution that an emulsified vegetable oil would. And then the final class of products would be solid products such as mulch, compost, shells, such as kite. So when you're installing a PRB with liquid carbon substrates, you're typically doing an injection wells or temporary injection points driven by a direct push. The advantage of the direct push points is that you really don't leave anything behind. So it's not going to have impact on someone's yard. The disadvantage is that you may have to come back in and add more material at a later time by direct push, whereas an injection well you can reuse. Solid carbon substrates are typically applied by trenching. Could be an excavator or one-pass trenching. You can also use large diameter boreholes and mix it in. So kind of a schematic showing the different types of PRB installations. The 4-foot trench, in orange, and then in green, the spacing of 10 foot between points using a soluble or slowly release substrate, and then 4-foot spacing for the backfilled material. Some of the benefits of the injection points: you can get a larger residence time, no depth restrictions, flexible locations. Longevity is going to be 3 to 7 years. And typically we want to set that back from the surface water because you don't want any of that material to get into the surface water. A trench, it's usually continuous, so there's some drawbacks from siting that. You don't, if there's utilities in the way, that makes it things harder to get a continuous trench. However, the longevity is going to be better, and you can't put it close to a surface water. There are depth limitations. Typical trench applications are limited to about 18 to 20 feet. You can use larger equipment to get down deeper. The other disadvantage is it has a small residence time. And then the backfilled material, no real depth restrictions. The longevity is going to be similar because you're using the carbon substrate typically. You can locate them close to the surface water. However, you're going to have a smaller radius and residence time, so you may have flow through and miss the backfill material. And then the other drawback is the longer installation time to install that material. So PRBs for total maximum discharge limits. So you're going to look for ways to treat the highest flux of nitrate. So that's based upon the concentration and the flow rate of the groundwater. You may not need to reach a very low concentration of nitrate. You may just be able to reduce those concentrations enough so that you control that material as it moves into the water bodies. So you want to treat the area with the highest nitrogen flux. And so how do you inject EVO? Typically, like for the emulsified vegetable oil that we sell, it's delivered toast to the site. It's you install a borehole with direct push injection rigs. You can either do it to a temporary point or a permanent well, and then you dilute the material with water prior to injection, and then you pump it into the ground. And these photos are courtesy of Jim Bagley, MT Environmental Restoration from one of the pilots that I'm going to talk about at Orleans in a little bit. So some of the challenges for the Cape Cod PRBs, regulatory acceptance and public concerns. You know, people say, are you injecting a hazardous waste? And no, it's not. It's food grade material. We're using soybean oil and food grade surfactants. One of the other concerns would be migration of oil or impacts to the surface water, and then permitting. We've had not really any issues with getting those things permitted on the Cape and other places. So implementation travel challenges, some cases you're going to have up to 70 feet of interval that you need to treat. On the Cape and other places, fast groundwater flow rate seepage velocity is going to require more substrate, and you also have high fluxes of oxygen nitrate. And in highly developed areas, access is going to be an issue. The injection materials are actually easier to just install because there you can change the locations as you need to. So it may require thousands of feet of PRBs. So one of the big questions is how long is it going to last, and how long do you have to rejuvenate? And those are questions that we're still working on. And you really need to understand the hydrology and the nitrate distribution up front before you design one of these PRBs. So I'm talking about 4 field demonstrations on Cape Cod and Martha's Vineyards that occurred between 2016 and 2020. Now we have 3 to 7 years of groundwater monitoring. First pilot was done at Orleans. Groundwater flow rates about 0.2 to 0.3 feet per day. Nitrate between 0.2 and 38 milligrams per liter, averaged about 12 milligrams per liter. In November 2016, a 110-foot PRB was installed. That's down at the bottom. 17 injection points, 10-foot spacing, 1 and 2 points, rows of points between 36 and 70 feet below ground surface. Injected about 2,600 gallons of EPO and 10,800 gallons total fluid. And we added some sodium bicarbonate as a buffer. Objective was to get greater than 3 years of resistance. We realized looking at the groundwater contours that we had material moving in from the west. So we extended the PRB to the north to intercept groundwater from the west. Again, it was a 110-foot PRB, 20 feet injection points, 10-foot spacing, 2 rows of points with about 3,700 gallons of EBO, which we included some lactate and about 950 pounds of sodium bicarbonate. So the results, we're seeing negligible impact at the EBO, 6 to 10 feet down gradient during injection, demonstrated persistence of the EBO greater than 6 years after the first injection, estimated the nitrogen flux reduction of about 0.6 kilograms nitrogen per foot per year, with nitrate concentrations of 10 to 25 milligrams per liter. Again, based upon the estimated flux, about 0.7 pounds of nitrogen removed per pound of SRS-NR. And you see over on the right results from one of the monitored wells. We're seeing, starting at around 16 milligrams per liter in November 2016. By June 2017, almost all the nitrate's gone, and it stayed very low over that 4-year monitoring point for this particular well. And we're seeing, DOC concentrations coming up in the negative ORPs. This is another graphic demonstration. On the left, you see the November 2016 nitrate concentrations in red. And then after the second injection of EPO, we're seeing very good treatment of the nitrate with only one well, MWB2050C, showing appreciable nitrate at that point, and that's just further away from the injection points. So conclusions, where the DOC was sustained greater than 4 milligrams per liter, you see an average of 94.5% removal of nitrate. DOCs persisted for more than 4.7 years, and it looks like up to 6 years. We don't have current data, monitoring data beyond that. And we didn't see any evidence that the DOC moved more than 50 feet from the injection wells. The next pilot is at Eastham, Massachusetts, a little bit faster groundwater flow rate of about 0.5 feet per day. Initial nitrate between 0.4 and 38, averaged about 5. Injections were done in 2020. It's a 200-foot long PRB with 21 injection points, one row of spacing 10 feet apart, and then the injection interval was 21 to 64 feet. Injected about 600 gallons of SRS-NR plus 264 gallons of sodium lactate to kind of jumpstart the process, and then the combination of sodium bicarbonate and calcium carbonate as buffers. Total injection volume is about 3,100,000 gallons. This is the results for the shallow well. The upper graph, this is the upground well, about 117 feet. We're really not seeing much change in the nitrate. We're not adding any TOC. 25 feet down gradient and M12SR, we're seeing TOC, our DOC levels get up to around 20 milligrams per liter, and the nitrate coming down and has remained down. We're seeing good results at 50 feet. However, at 100 feet down gradient, really not much DOC, a maximum of about 4 milligrams per liter, really no change in the nitrate. So, you know, it looks like we're getting good denitrification down at least 50 feet below the PRB. And then the intermediate zone, again, in the upper slide, there's the background locations, and then we're seeing a little bit higher DOC in this particular location, up to around 40 milligrams per liter of DOC, and again, complete removal of nitrate at 25 and 75 feet, and not so much at 175 feet down gradient. So conclusions from Eastham: the DOC sustained greater than 5 milligrams per liter over 2.4 years, works for low nitrate concentrations, average removal of 92% of the nitrate in the shallow zone, and up to 70% in the, or 95% in the intermediate zone, 75 feet down gradient. Didn't show you the data, but we do see the buffer increase the pH up to 25 feet down gradient in the shallow zone and 100 feet in the intermediate zone. The next project is Falmouth. This was funded through a 2000 Southeast New England program grant from EPA. It was a animal property owned by the town of Falmouth. They had previously done some injections or investigations to try to figure out where the nitrate flux was occurring. We thought this was going to be a higher groundwater flow rate of about 2 to 3 feet per year. Actually, and involved in the process, we're only at around about 0.15 to 0.25 feet per day. The pH is fairly low, between 4.3 and 6. So we had two dosages that we applied. We were looking to see failure within a 2-year monitoring point. We do have data showing that it's still being effective. And then we have multi-level sampling wells, and we're also looking at some of the secondary groundwater quality parameters. So the design, initial nitrate between 0.3 and 28 milligrams per liter, averages about 4.5. Again, multi-level sampling points at 3 to minus 44 feet mean sea level. April 2020 injections, 120-foot PRB, 12 injection points, one row of spacing, 10 feet apart, and then 21 to 64 feet below ground surface for the injections. The 1-year side of the PRB was 60 feet long. We added about 1,100 gallons of SRS-NR, some calcium carbonate, and a total injection volume of about 6,300 gallons. So there's a monitoring well, Hui 1, which is up gradient, Hui 3 within the PRB, Hui 5, 15 feet down gradient, and MTER 6A, 125 feet down gradient. In the 2-year demand, we have 6 injection points, again, over the same spacing, but the almost twice as much SRS-NR, 2,100 gallons, and again, in the same volume of total volume. And here we're looking at up gradient well, Hui 2, 12 feet up gradient, Hui 4 within the PRB, Hui 6, 17 feet down, and Hui 8, 64 feet down gradient. So this is the results for the 1-year pilot demand. And so we're looking at nitrate concentrations with depth at 3 different intervals of time. So June to July 2020 is before the injections, November 2020, about 4 months after the injections, and then May 2022. You see that there's ranges between, say, 1 to 15 milligrams per liter of nitrate initially, and we're not really seeing much change in November 2020. The orange point Hui 3 is in the PRB, and we don't really see any evidence that the EVO reached that point between the 2 injection points. In May 2022, we're not seeing much evidence for denitrification in the PRB or 15 feet down gradient, but MET R6A 125 feet down gradient, we are seeing good removal, particularly at the shallow depths. And this particular area of the site had a finer grain soil sequence, so we're not able to achieve as much distribution of the EVO in that injection zone. In the 2-year demand, we're seeing again at the top and brief injections, and then by November 2020, we're seeing good removal in the 17 feet down gradient and 64 feet down gradient, and that's maintained probably not quite as throughout the depth interval, but we are seeing good removal between say -5 to -15 feet mean sea level. So the conclusions from Valmont is 1-year demand had limited EVO and denitrification observed in the well 15 feet down gradient. We do see denitrification occurring 125 feet down gradient. The 2-year demand, we're seeing denitrification observed in the well 17 feet down gradient of depths between 4.7 to 12.7 mean sea level, and 64 down gradient at roughly 4.5 to 6.5 feet mean sea level over 1.8 years. The buffer increased the pH up to 125 feet down gradient of the 1-year PRB and 64 feet down gradient in the 2-year PRB. We're seeing consumption of dissolved oxygen, production of dissolved iron, manganese, and arsenic. The 4th pilot is Martha's Vineyard, a little bit higher groundwater flow rate, concentrations of nitrate between 0 and 12, averages about 3. These injections were occurred in November 2020, 150-foot PRB. This PRB was located with 80 feet from Lagoon Pond, so that's pretty close. Used 12 injection points, 1 row of spacing, 10 to 15 feet between the points, and then a little bit shallower injection interval between 4 and 22 feet. Here we injected about 3,400 gallons of SRSNR, 1,600 pounds of calcium carbonate, and a total injection volume of about 17,000. So some of the results here, you see the yellow and orange lines are upgraded wells, and then on the left side you see wells 22 and 35.5 feet from the PRB. The nitrate's coming down and stayed down over the monitoring period. So good nitrate removal downgraded of the PRB. One of the things that they've done at this site was to look for the accumulation of nitrogen gas. So they did that with evaluating the nitrogen to argon measurements using a high precision membrane inlet mass spectrometer, and gradient PW3D, fairly low ratio, and then W5, the ratio of N2 to argon is much elevated, so showing that in fact we were completely converting a nitrate to nitrogen gas. One of the questions that we still haven't resolved is what happens with some of the greenhouse gases that are produced during denitrification, the nitric oxide and nitrous oxide. And so that's something that is going to need to continue to be evaluated. So conclusions from Martha's Vineyard: this PRB was located about 80 feet from the water body, had minimal impact on the surface water, complete conversion of nitrate to nitrogen gas, estimated to remove 91% of the nitrogen, or about pounds per linear foot of the PRB. As part of the Falmouth project, we were funded to do a permereactive barrier for removal of nitrate from groundwater through injection of emulsified vegetable oil engineering design manual. So that's cooperation between Woods Hole Oceanographic Institute, Isotech, and Terra Systems. So it's available at the location here at one of the Terra Systems website. So when you're designing a PRB, you need to consider where the location, where to put it, so that you're reducing nitrogen loss while achieving the attainment of that watershed specific targets. So you need to know the concentration and the flow rate. Typically PRBs are installed perpendicular to groundwater flow. You need to be able to get access to the property and consider the land usage. The other things you might want to consider would be if there's a downgradient potable well, or how close it is to proximity to the surface water body. So PRB designs, looking at the length, again, perpendicular to groundwater flow, typically identify where the PRB would support the watershed targets for nitrate. You need to have access to identify where the PRB, where the nitrate's flowing through in that vertical interval, and the width. You know, as the column study that was performed for Gonzalez, we saw a tenth of a day was enough time to see good degradation of the nitrate. Although typically we're going to recommend 7 to 14-day resident time to account for variation in the groundwater flow direction and hydraulic conductivity. So the EVO dosage, again, it's going to be dependent upon the groundwater flow rate, the dimensions of the PRB, the length and width and height, the nitrate concentrations, competing electron acceptors. Many of these aquifers with the high groundwater flow rate is going to have elevated dissolved oxygen. Sulfate's going to be present, and it's going to depend upon the groundwater conditions as to how much sulfate's going to be there, and it can be an important electron acceptor. And then ferric iron that's typically associated with the soil is going to be converted to ferrous iron, and so you may see some ferrous iron being produced. So you want to avoid overdosing and avoid underdosing. Overdosing to give you the longevity that you're looking for. If you overdose, you may get lower pH. You may mobilize metals like iron and arsenic, and you may also generate methane. In some of our other projects that we've looked for the presence of methane after an EVO injection, what we typically see is that the methane that's generated may accumulate the water table, but then as it moves up into the vadose zone, where there's aerobic conditions, that methane is consumed. So when you're doing monitoring for a PRB, you're looking for nitrogen species, nitrate, nitrate, ammonia, and total Kelp log nitrogen, TKN. You want to monitor total organic carbon or dissolved organic carbon. Monitor fuel parameters such as pH, ORP, dissolved oxygen, and temperature. On a secondary list of analyses would be sulfate, the metals, the iron, manganese, and arsenic, phosphate. And then in tertiary analyses that are not as critical, but useful to have would be things like methane, look for the denitrification functional genes, and also the greenhouse gases. So in conclusions, it's a smaller PRBs or smaller capital costs than sewer and wastewater treatment, can address point and non-point sources of nitrogen or the aquifer. PRBs can treat nitrogen near to a point of discharge and can result in immediate improvements to surface water quality to reach a TMDL. Typically, it's going to be a smaller footprint with just minimal disturbance, limited primarily to the installation without any ongoing maintenance required. Can be used in combination with other removable techniques for achieving a TMDL. It gives you time to fund, design, and build a wastewater treatment. And in communities on the Cape and in other places, we're looking at between 5 to 2,000 feet of PRBs. In some cases, up to 30,000 linear feet of PRB might be needed to address a larger town. I'd like to acknowledge some of the people that have worked on this project with us, Matt Charette and Paul Henderson from Wood Hole Oceanographic Institution in Falmouth, Christian Retchen, also from Falmouth, worked for ScienceWares, involved in that HUI project on Falmouth. Jim Bagley from MT Environmental Restorations, Tom Clarice, who's now retired, Mark Owens and Julian Marion from AECOM, worked on the Orleans project, Jessica Thomas and Brian House, worked on the Martha's Vineyard project. They're from the SMAST at the University of Massachusetts, Dartmouth in New Bedford. I'd like to acknowledge Brian Howe's contributions. Unfortunately, he passed about 2 years ago. And then finally, Brooke Paulson and Doug Healy from Verdantis, formerly ES&M, and Norton, Massachusetts, worked on the project at Eastham. And at this point, I'd like to take any questions. Thanks for listening.
Thank you so much, Mike. That was a great presentation as always. We do have a few questions from the audience, and if people have additional questions, if you can enter them into your GoToWebinar control panel, we'll get through as many of them as we can over the next 10 or so minutes. So the first question for you, Mike, is during the column studies earlier in the presentation, can you talk about the pore volumes that were being tested?
I don't remember those numbers off the top of my head. I know that for the third column, we did look at pore volumes. So, we were up around 250 pore volumes at that high groundwater flow rate, a relatively short column. Most of the other ones, I think we operated for probably 100 pore volumes or thereabouts. And, the first column study was done for well over a year. So that was a pretty extensive treatability study.
Great. And there was a link that you put just a couple of slides back that you displayed in the slide. Do you mind to put that back on there so that I can share that in the chat with everyone so that they can download that link?
The Denitrification PRB design manual?
Yep.
Okay.
I'll put this in there. And then while I'm doing that, the next question for you is, could you advise what would be the approach if there is nitrogen ammonia present to start with? This is the first part of the question. And then 2, have you established a maximum nitrate concentration present that would be toxic for the denitrification process to occur?
So we have ammonia and nitrogen. So typically for a septic system, when it leaches from the septic field, it's going to have a lot of ammonia, and that's going to get converted under aerobic conditions to nitrate. We have not done a lot of work looking at what happens to ammonia in PRB, either in the column studies or in a field pilot. But I would expect, to see some uptake of nitrogen or ammonia by the bacteria. It's still an open question. As far as the maximum concentration of nitrate, it being toxic, I don't think that there is. If you're dealing with a fertilizer plant and you've got really high concentrations of nitrate, it just means that you're going to have to add more substrate to get that to go. But I don't think there's going to be any upper limits on toxicity.
Yeah, I would definitely agree with you on that because we've seen a lot of sites where a lot of fertilizer has been applied and we haven't seen, any inhibition of the nitrogen cycle as long as the other necessary components are there for the microorganisms. Okay, so another question for you, Mike. Can you talk about the risk of stalling at nitrite, which might have a lower groundwater quality standard?
In the 4 pilots that we have seen some nitrate being produced, but we've not seen any evidence that it persists. So, I think that, unless you have really extreme conditions, that, the nitrate's going to go to nitrite and then on to nitrogen gas.
Great. And there are a lot of comments about how great this presentation was, Mike, and that they appreciate you sharing it. And there are questions if you would be willing to share PDFs of the presentation. Is that something that we can share with the audience?
Yes, it is.
Okay, great. So if anyone has a request for a PDF of the presentation, you can reach out to us at info@microbe.com and we'd be happy to send over a PDF of it. We'll get that from Mike. Also, sometimes it takes a minute to digest all the information because Mike has given you some great case studies. So if you have questions that come up, you can always feel free to reach out to Mike and Dick. They're a great resource directly. I'm sure they'd be happy to talk to you. And if it's something on the biological side that you want to think about the microorganisms and the testing that can be done, you can reach out to us also at info@microbe.com and we'd be happy to talk to you about that and answer any questions that you have. So it looks like most of the comments I'm seeing right now, Mike, are just how much they appreciate this presentation, and it's really good information that you've provided that's valuable to the industry. So I don't think that we have any other questions to address. So I just want to personally thank you. I know you're very busy, and so I appreciate that you and Dick take time to really share your wealth of knowledge and experience in the industry. It's definitely valuable for us at Microbial Insights, and I know for everyone that is working in remediation. So we value our relationship with you, and thank you very much for your time and the presentation today. And for the audience, we want to thank you too for being here and taking time out of your schedules to listen to this. And we will have the recording available on the website by the end of the week that you'll be able to watch this again and get all this great information that Mike has provided. So, if there's anything else you want to say, Mike, as a summary, we have a couple minutes left before we close out.
Just thanks to Microbial Insights for giving us this opportunity.
All right. Well, thank you, everyone, and I hope you have a wonderful day. And if you have questions, reach out to us, and we look forward to hearing from you. And thank you again, Mike and Dick. We really appreciate you both.
All right. Thank you.
Thanks.